Imagine standing at the base of one of those colossal electric transmission towers, held steady by this whole network of cables. Or picture the immense foundational stability of like a soaring skyscraper. These everyday marvels, they seem complex, right? But they all hinge on a deep understanding of forces. So today we're taking a deep dive into force vectors, the absolute sort of building blocks for understanding how things stay put, how they move, and what makes them stable, or maybe not so stable.
Yeah, and what's truly fascinating here, I think, is how systems of forces, which can look really intricate, can actually be broken down, analyzed, and understood using a surprisingly elegant set of rules. Our sources, including a really comprehensive textbook chapter, they lay out these principles quite clearly. Oh, so this deep dive isn't just about knowing about force vectors. It's kind of your shortcut to truly understanding their significance and how they're applied in the real world. We'll unpack how to define, combine, and analyze these, crucial elements of engineering mechanics, and hopefully sprinkle in a few aha moments along the way.
Okay, let's unpack this then. Before we even think about combining forces, we need to understand the fundamental language, right? What we're dealing with. Our sources kick off with a distinction that's, absolutely foundational.
Precisely. In engineering mechanics, many physical quantities are either scalars or vectors. Now, scalars are pretty simple. They're quantities defined purely by their magnitude, just a number, positive or negative. Think about something like length or mass or time. If I tell you an object weighs 5 kilograms, well, you have all the information you need right there.
Right. No direction needed there. Makes sense.
Exactly. But here's where it gets really interesting. Vectors. Vectors demand both a magnitude and a direction for their complete description. Forces, position in space, moments. These are classic examples you run into in statics. Visually, think of a vector as an arrow. The longer the arrow, the greater its magnitude. The way it points tells you its direction. And that arrowhead, that's its sense, like is it pushing forward or pulling backward, something like that. For notation, you'll often see them bolded in print like A and their magnitude italicized A. If you're just, scribbling notes, it's common to draw a little arrow above the letter.
Okay, so we have these arrows, representing forces with magnitude and direction. But the real world rarely has just one single isolated force acting. How do we start manipulating them, combining them? Like building with Legos, I imagine it starts with some basic moves.
It absolutely does. And the core operations really highlight the unique nature of vectors. First up, multiplication and division by a scalar. If you multiply a vector by a positive number, say 2, its magnitude simply doubles. Same direction, just longer. But, and this is key, if you multiply it by a negative scalar, say -1, not only does its magnitude scale, but its directional sense flips. It points in the exact opposite direction, 180 degrees around.
So hang on, if I have a force pulling to the right and I multiply it by, -2, it's now twice as strong but pulling exactly left.
You've got it. Exactly. Then we move to vector addition, which is, fundamental for combining forces. The parallelogram law is the classic way. Imagine you have two forces, let's call them A and B, acting on the same point. To find their combined effect, their resultant R, you first join their tails together. Then you complete a parallelogram. You draw a line parallel to A, starting from the tip of B, and another line parallel to B, starting from the tip of A. Where those lines intersect forms the opposite corner of the parallelogram. The diagonal stretching from the original point where the tails met out to that opposite corner, that diagonal is your resultant vector R.
Huh. That's actually a pretty clever way to visualize the combined effect.
It is. And the triangle rule is a fantastic shortcut, often more convenient. Instead of drawing the whole parallelogram, you just add the vectors head to tail. So you draw vector A, then place a tail of vector B right at the head, or tip, of A. The resultant R then stretches directly from the tail of your first vector, A, all the way to the head of your last vector, B. It closes the triangle. It's basically derived from the parallelogram law, just a bit cleaner to draw sometimes. Oh, and just like regular numbers, vector addition is commutative. You can add them in any order. A plus B gives you the exact same resultant as B plus A. Also, as a special case, if two vectors happen to be collinear, meaning they lie on the same straight line, the parallelogram law just simplifies right down to simple algebraic addition. You just add or subtract their magnitudes depending on their senses.
Okay, addition makes sense. And subtraction, does that get complicated?
Not at all, actually. Vector subtraction is really just a special case of addition. Subtracting vector B from A, B is exactly the same as adding negative B to A plus B. So you literally just flip the direction of B, make it A, B, and then add it to A using the same parallelogram or triangle rules we just talked about.
Okay, cool. So we know how to define a force as a vector and how to combine or subtract them geometrically using these diagrams. What does this actually, mean for real-world forces? How do engineers use these rules to figure out what's really happening in a bridge or a building?
Well, that's the crucial link. Experimental evidence, gathered over centuries really, confirms that force behaves exactly like a vector. It has magnitude, direction, sense, and it absolutely combines according to that parallelogram law. This leads us to two very common types of problems in statics, the study of forces in equilibrium. First, finding a resultant force. If you have, say, two forces acting on a hook, like two ropes pulling on a single point, you can combine them using the parallelogram or triangle rule to find their single equivalent combined effect, the resultant FR. Once you've sketched that force triangle, you then use standard trigonometry, the law of cosines and the law of sines, to precisely calculate the exact magnitude and direction of that resultant force. For example, our source mentions a screw eye pulled by a 100 Newton force and a 150 Newton force at specific angles. Using the rules, they find the resultant is about 213 newtons acting at roughly 55 degrees.
Okay, finding the total effect. And the second type of problem?
That's finding the components of a force. Sometimes you know the total force acting, but you need to understand how much of that force is acting along specific, maybe useful directions. Like if you're pulling a crate diagonally, how much of your pull is actually moving it forward, and how much is just, say, trying to lift it slightly. You resolve the main known force into two components acting along specific axes you choose, often called the U and V axes in examples. You essentially reverse the parallelogram idea. Start with a known force vector, and from its tip, draw lines parallel to your chosen component axes until they intersect the axes themselves. This forms a parallelogram where the sides represent your force components. And again, the law of sines is typically used here to calculate the magnitudes of those components.
Okay, wait. This raises a question that always makes me pause. I've seen examples, maybe like the one you mentioned, where a component force can actually end up being larger in magnitude than the original resultant force you started with. How? How is that possible? How can a part be bigger than the whole force? It sounds like breaking physics.
Yeah, that definitely sounds counterintuitive at first glance. It's a fantastic observation, though. It's not breaking physics. It's actually revealing something important about geometry and direction. Think about it this way. Imagine you need to push a very heavy box across the floor, but there's a narrow gap you have to push through, forcing you to push almost sideways, barely nudging it forward. The total force you exert along your arms might have to be massive, right? But the effective component of that force actually pushing the box forward might be quite small. Conversely, if you resolve a known force into components along two axes that form a very acute angle, that's the 90 degrees, the geometric construction, the parallelogram, can result in sides, the components, that are longer than the original diagonal, the resultant force. It's all about the angles involved. It tells you that to achieve a certain effect in one direction might require a much larger force if it also has to act significantly in another, less useful direction simultaneously. Does that make a bit more sense?
Ah, okay. Yes, picturing that narrow gap push helps. So it's about the directions you're projecting the force onto.
Got it. So drawing these diagrams for two forces works, but what if you have, say, 5 different cables pulling on that same hook? I guess drawing complex chains of parallelograms or triangles over and over would get pretty tedious and maybe inaccurate fast.
You've absolutely hit on the exact limitation. While you could, in theory, apply the parallelogram repeatedly, add F1 and F2, get a resultant, then add F3 to that resultant, and so on, it quickly becomes an incredibly laborious geometric and trigonometric calculation, prone to errors too. And that, my friend, perfectly sets the stage for a far more efficient, really powerful analytical approach.
Okay, this sounds like the moment things get maybe less visual and more mathematical, moving from drawing diagrams to maybe a more powerful analytical method that simplifies things, especially with multiple forces. This must have been a huge leap. It absolutely was. It's where things get really elegant, especially when forces all lie in the same plane. We call them coplanar forces. We can resolve each force into rectangular components along standard perpendicular x and y axes. Forget drawing complex angles for a moment. You use simple trigonometry. The x component of a force F, let's call it Fx, is just F times the cosine of the angle u it makes with the x-axis, F cos u. And the y component, Fs, is F times the sine of that angle, F sin u. Sometimes, if you know the slope, like a 3, 4, 5 triangle representing the force's direction, you can use simple ratios to find the components too, avoiding angles altogether.
And those components, Fx and frac, can they be negative, like if a force points left or down?
Great question. Yes, absolutely. For the calculation part, Fx or phi can definitely be negative scalars. That negative sign simply tells you the component points along the negative axis direction, like left for x or down for y.
Hmm.
Graphically, the arrow direction shows it, but mathematically, the sign handles it. Now, enter Cartesian vector notation. This is where we introduce those helpful dimensionless unit vectors, I pointing along the positive x-axis and j along the positive y-axis. This lets us write any force F really neatly, as F is fxi plus fyj. The big advantage here is it cleanly separates the magnitude and direction for each component within one expression.
And this is the aha moment you mentioned earlier for dealing with lots of forces in a plane.
This is the game changer. Seriously, to find the resultant of several coplanar forces, maybe 3, 4, 10 forces acting on that hook. Step 1. Resolve every single force into its x and y components using that Traeger slope method. Step 2. Now, just algebraically sum all the x components together. Pay attention to the signs. This gives you the total resultant x component. Let's call it f of x. Step 3. Do the exact same thing for all the y components. Sum them up algebraically to get fry. Step 4. You now have the total x and y effect. To find the magnitude of the overall resultant force Fr, you just use the Pythagorean theorem. Fr can force a squirt, Fr by 2 plus Fry2.
Okay.
Step 5. And to find its direction, the angle it makes with the x-axis, you use the inverse tangent. 2a equals tan-1 Fryx.
Wow. Okay. So instead of drawing multiple complex parallelograms and wrestling with law of sines and cosines over and over, you just break every force down into x and y bits, add up all the x bits, add up all the y bits, and then use Pythagoras and tan to put the final answer back together. That is a massive shortcut.
Exactly. It transforms what could be a really tedious geometric puzzle into straightforward algebra. It's vastly more convenient, less prone to error, and just way more efficient for analyzing systems with multiple forces. It's the standard analytical method.
Okay, we definitely got a handle on 2D now, but, the real world isn't flat. What about forces acting in 3 dimensions? Does it stay this neat, or does it suddenly get horribly complicated again?
This is precisely where that Cartesian vector form really comes into its own. It extends beautifully to 3D and simplifies things immensely compared to trying to visualize 3D parallelograms, which gets messy fast. First, we need a standard coordinate system. We use what's called a right-handed coordinate system. Quick check. Point your right thumb along the positive z-axis, often pointing upwards. Your fingers should naturally curl from the positive x-axis towards the positive y-axis. It's just a convention everyone agrees on, so results are consistent. Any vector A in 3D can then be broken down or resolved into 3 rectangular components along the x, y, and z axis. Ax plus x plus A plus a's.
Right, makes sense. So instead of just I and j, we now need a third unit vector, probably k for the z-axis.
You're exactly right, one step ahead. We introduce I, j, and k as the dimensionless unit vectors pointing along the positive x, y, and z axes, respectively. So any 3D vector A can be written super cleanly as A equals xi plus ayj plus ask. Again, this notation is powerful because it keeps the magnitude and direction for each axis component separate but tied together. And finding the overall magnitude of this 3D vector, still pretty straightforward. It's just the 3D version of the Pythagorean theorem. A equals 2 plus AA2 plus A is 2. You square each component, add them up, and take the square root.
Okay, magnitude is fine, but how do you describe its specific direction in 3D space? That sounds tricky. Just one angle isn't enough anymore, right?
Correct. One angle isn't enough. It's actually quite elegant how it's handled. We use 3 coordinate direction angles, usually called alpha, beta, ag, and gamma. Alpha is the angle between the vector and the positive x-axis. Beta is the angle with the positive y-axis. Gamma is the angle with the positive z-axis. These angles are always measured from the tail of the vector and fall between 0 and 180 degrees. Now, the cosines of these angles, cosine, 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 are particularly important. They're called the direction cosines. And here's the neat part. These 3 direction cosines are precisely the x, y, and z components of the unit vector that points in the same direction as our original vector A. Remember, a unit vector UA is just AA. So UA tos to I plus cosine A plus cos ij plus cos A plus ij. There's also a cool relationship. Cos 2 goes cos 2 goes plus cos 2 go 1. If you square each direction cosine and add them up, they always equal 1. This tells us the 3 angles aren't fully independent. If you know 2, you can actually calculate the third. And the best part for practical problems, adding Cartesian vectors in 3D is just as simple algebraically as it was in 2D. If you have A and B, their resultant R is just Rx plus Bxi plus AY plus BJ plus AS plus BCK. You just add the corresponding components. This generalizes perfectly for finding the resultant of many concurrent forces in 3D, like figuring out the total pull on a pole from multiple guy wires.
That is incredibly powerful. It keeps the complexity manageable even in 3D.
Okay, we've talked a lot about forces and how to represent them. But how do we describe the actual location of things in that 3D space? Like, where exactly is the anchor point of a cable, or how do we define the specific line that a force acts along?
That's where position vectors come in. They are absolutely fundamental for locating things in space. A position vector, often denoted by r, is essentially a fixed vector, an arrow, that locates one specific point in space relative to another point. We still use our right-handed XYZ coordinate system. Often the z-axis points straight up, like towards the zenith, and the XY plane is horizontal. Any point in space can then be located by its XYZ coordinates, for instance. Point A might be at 4 meters, 2 meters, -6 meters.
So it's like giving a unique address, a 3D address, to every important point in an engineering problem.
Pretty much, yeah. It's a precise way to map things out. A position vector, starting from the origin 0, 0, 0, and going to a point, p, x, y, z, is written very simply as r, xi plus y, j plus zk. Its components are just the coordinates of the point. But more generally, and often more usefully, we need a position vector between two arbitrary points, say from point A to point B. To find this vector r, you subtract the coordinates of the starting point, the tail A, from the coordinates of the ending point, the head B. So the vector r from A to B is r equals xb xai plus yby j plus cb zak. You can think of it as, how far do I need to travel purely in x, then purely in y, then purely in z to get from A directly to B? This calculation gives you that directed path. One of the examples uses this to find length and direction of a stretched rubber band between 2 points. Now, a really crucial application of this is defining a force vector directed along a specific line. Very often in problems, you know the magnitude of a force, like the tension in a cable, but its direction isn't given by angles. Instead, it's defined by 2 points that its line of action passes through. Think of a force F acting along a cable stretching from point A to point B. That force F must have the exact same direction and sense as the position vector r that runs from A to B. So the process is, first, find that position vector r using the coordinate subtraction we just talked about. Second, find the magnitude of r, its length. Third, create the unit vector u that points along that line by dividing the position vector r by its magnitude, us or rr. This u vector captures only the direction from A to B. Finally, you multiply the known magnitude of the force F by this unit vector u. That gives you the complete force vector, Fu equals FRR. This technique is used all the time by engineers to determine the vector representation of forces in cables, supporting roofs, bridge towers, or even, as one example shows, a person pulling on a cord attached between 2 points.
That is incredibly elegant. It connects the geometry, the location of points, directly to the direction of the force vector itself. Seamless. Okay, finally, we arrive at something you mentioned earlier, what some might call the Swiss Army knife of vector operations, the dot product. What exactly is this thing, and what kind of powerful tricks can it do for us?
The dot product? Yeah. It's also sometimes called the scalar product, and that name gives a clue. It's a specific way to multiply 2 vectors, A and B. But here's the key difference. The result isn't another vector. It's a single number, a scalar. The classical definition involves the angle between the vectors. A dot B, written AOB, is defined as the product of their magnitudes, A times B, multiplied by the cosine of the angle U between their tails. AOB equal AB cos U. That angle U is always between 0 degrees and 180 degrees. But, and this is why it's so useful in practice, if you have your vectors A and B already in Cartesian form, AXI plus AJ plus SK, calculating the dot product becomes incredibly simple. You just multiply the corresponding x components together, multiply the y components together, multiply the z components together, and then add up those 3 products algebraically. So AOB equals XBX plus AB plus SBEs. That's it. The result is just a number, which can be positive, negative, or even 0.
Okay, interesting. So it boils 2 vectors down into a single number. But why is that so useful? What's the practical power behind doing that? What does that number actually tell us?
That's the really important question to ask. Its power lies mainly in 2 incredibly useful applications that pop up all the time in mechanics. First, it's fantastic for finding the angle between 2 vectors or 2 intersecting lines, especially in 3D, where just looking at it can be really deceptive. Since you know the definition AUB equal quotients U, you can easily calculate AU using the component multiplication, and you can easily calculate the magnitudes A and B. So you can just rearrange the formula to find the angle. U cos 1, AUB, AB, gives you the angle directly. And here's a really neat insight connected to this. If the dot product of 2 non-zero vectors happens to be exactly 0, AUB other 0, what does that tell you about cos U? It must be 0, which means the angle U must be 90 degrees. So a 0 dot product is a super quick way to check if 2 vectors or lines are perpendicular or orthogonal to each other. Invaluable check for engineers. Okay, in the second major, equally critical application is finding the component of a vector acting parallel to a specific line or axis. This is absolutely essential for figuring out how much of a force is actually doing useful work along a particular direction, like how much of the tension in an angled cable is actually supporting a vertical load, or how much force is pushing along a beam. The magnitude of the component of vector A that acts parallel to a line, where the line's direction is defined by a unit vector UA, is found simply by taking the dot product. AA equals AEUEA. Remember, since UA has a magnitude of 1, this is just A1 cos U, which is the projection of A onto the line. This scalar result AA, if it's positive, tells you the parallel component acts in the same direction as YA. If it's negative, it acts in the opposite direction. And if you want to represent this parallel component as a vector itself, you just multiply that scalar magnitude AA by the unit vector UA. A vector equals AEA.
Yeah.
Then if you need the other part, the component of A that's perpendicular to the line, you can find it easily using vector subtraction. The perpendicular part is just the original vector minus the parallel part, M-terp equal AA vector. This is exactly how engineers figure out the force acting along a specific structural member versus the force acting perpendicular to it, which helps analyze stress and potential bending.
Wow, okay. So what does this all really boil down to? We've gone from just defining a scalar, like mass, to understanding vectors with direction, adding them with parallelograms, simplifying that with x and y components, extending it all into 3D with I, j, k, locating points with position vectors, and now even using the dot product to find angles and projections. We've covered the essential language of force vectors. It feels like you now have this really comprehensive toolkit, a way to describe, combine, and break down forces to truly understand stability and motion in pretty much any situation. It really does feel like a shortcut to being properly informed about a fundamental area of mechanics.
Absolutely. And this truly foundational understanding of vectors, it underpins almost every engineered structure you see, every complex movement a machine makes, every single decision about strength, load bearing, and stability. Think back to those transmission towers we started with. Every single cable, every connection, every angle is calculated using these vector principles to ensure it can withstand the forces of wind, ice, and its own weight. Or think about the precise, intricate movements of a robotic arm in a factory. That's all controlled and calculated using vector kinematics and dynamics. So this raises, I think, an important question for you, the listener, to consider now. The next time you see a suspension bridge with its elegant cables, or a construction crane lifting a massive beam, or even just something simple like pushing a heavy shopping cart up a ramp, can you now start to visualize that invisible dance of force vectors at play? Hopefully, you're now seeing that world through a much more informed lens, where every push, every pull, every static structure reveals this hidden network of vectors, all working according to these elegant rules, literally holding our engineered world together.